So in this part, we want to diagonalize the Hamiltonian of the complex scalar field theory that we have here. And for that, it turns out that the correct way to express the field operator in terms of the what I will call a creation annihilation parameter A and B is the following. So I introduce a so this is actually the Fourier transform of the field, but so omega p is according to Peskin and Schroeder just the energy of the field, and so A p here E minus px plus B p dagger E I px. So that is the correct way to write this field, so that at the end A and B are indeed annihilation operators, and A dagger and B dagger are creation operator. At the end, we will see that all charges match what we expect. So we want to express the temporal derivative of this field. So let's just compute that. So I will put a factor minus I here, and so we have the energy, so MP, and then simply so AP, and now we have a minus here. Okay, we can simplify a bit. And one thing that is good to do is to make a change of variable in this term here, transforming p into minus p, so that we can factorize the exponential terms. So I'll do that straight away. So here we can simplify, so we have p over 2 minus I, and here AP minus B minus P. And here we have the common factor E by X. Okay, so that's phi dots. So the same trick here, in order to factorize the exponential, we can do here. So I will write it. So phi of X is and simply AP plus BP dagger, B minus B, that's the full point, minus B, exponential minus APX. Okay, so we have this two quantity here, that's one, that's two. We also need the conjugate of this quantity, but okay, that's something that we can just compute on the spot when we need them. So from that, we can directly introduce, substitute these expressions into the Hamiltonian. So we will have a special derivative. I will introduce two momenta, so one that's P, and one that's, let's say, Q. Okay, so the first term is phi dot star. So this is this term here. So that's phi dot. So that's the first one. That's so the first field I will associate the momentum P, and the second field in the product I will associate Q. So for the first term we have this, so the minus I will disappear, because we'll have minus I here, but from the star version we'll have I, so that's plus 1. So we just have omega p, omega q divided by 4, and well, simply the operators now. So AP minus B minus P, and the star version of that, but with the Q momentum. So that's AQ dagger minus B minus Q. Okay, and the exponential factor is E minus I P minus Q X. Okay. Now for the second term, so the second term involves the spatial derivative of phi and so phi dagger. So phi is here. We will use this expression. So the spatial derivative will just bring out a factor minus IP. That's it. So actually, there's also a factor, so the zero component will give us a factor exponential minus I omega p minus omega q. I will not write it, we should, but in the end we will see that p has to be equal to q, and therefore this factor will just be equal to 1. So I will just forget about it here, but it's true that we should actually write it. It's there. So, yeah. So that's plus 4 omega p, omega q. And so the spatial derivative of the first term so the first term is star, okay, so it will be IPX, so it will just give us IP. And the second term will give us minus IQ. Okay. And then we just have the operators, so A, B, star, because the first term is star minus P dagger, so here there's no dagger. So this term here is simply this one here, dagger. Okay, and the second term is, well, this one without the dagger and with the Q momentum. And for the exponential factor, it's now, it has an opposite sign compared to the previous one, minus QX. Okay. And then we have the last term, which is just m square, phi square phi. So that's quite easy. That's just m squared for omega p, omega q. And the operator is actually the same as this one here. So this part is not there, of course, but the operator is the exact same as this one, and the exponential factor as well. So I won't write it. So we now have this expression, which we can quite easily simplify by simply taking the x integral, because we see that the only x dependency is in this exponential factor here. So this will give us a 2 pi cube delta p minus q term. So I just write it like this, but this is what the x integral generates, and I can use that directly in order to simplify the q integral. So this factor here will compensate this one, and yeah. So in the end, we just have d3p 2 pi q. I used the delta in order to simplify all of that. So here we have omega p over 2. time this operator here, so AP minus B dagger, AP minus B minus P. And the second term, so as I said here, so this term is the same, so we can actually factorize that. This is just now P squared, and P squared plus M squared is actually omega P squared. It's the on-shell energy of the field. So we actually have here a factor omega P squared over 2 omega P. So this is actually the same factor as this one here. And then the operator, so AP dagger plus B minus P, and AP plus B minus P. So, so this just simplify here. And okay, so we are just left with this. So there's a plus sign here. We just left with this expression, which we can easily simplify. So d3p 2 pi cube. So we have this factor omega p over 2. And then we can just distribute these two factors, AP dagger. Now in the second term we actually have AP dagger AP. Then we have, so I will just take the BB term, so then we have B. So it's actually, so if I take this term, it's minus P, but I can make a change of variable and just call that P. So that's plus P dagger BP plus, for the second term, BP dagger. So we have the same structure here with A and B. And the cross terms actually vanish because, so you see this term will be compensated by this term here. Okay, because they commute. So that's the only non-trivial terms that we have. And what we can do is to write that as, so, I mean, let me just write it there. So if I just take this, these two A2 terms, okay. So the first one we recognize as the number operator, from quantum mechanics. So that's the number operator for the particle that's created by the operator A dagger. But we have the second term here. But the second term, we can write it as simply AP plus AP dagger. Okay, and we can do the same for this term here, which is just BP dagger BP plus BP dagger. So in the end, what we have is, so this term here is the same as this one, so we have a factor 2 and the same here. So factor 2 can be absorbed somehow, and that's just black. Omega P, and we have therefore AP dagger plus BP dagger. Now we have extra terms. The extra terms that we have are these commutators, which are actually infinite, okay, infinite numbers, but this is an energy that we can reabsorb somehow in the definition of the field, or we can see later as well that with what we call the normal products, we can get rid of them. So physically it's okay because those are constant terms, and even though they are big, in experiment we just measure difference of energies. So for now on, we will just forget about this constant term, and therefore our final result is this. So how to interpret that? Well, so that's the Hamiltonian, and well, it's very easy. What it says here is that the Hamiltonian is simply the sum over all modes, okay, of the energy of a given mode times the number of particles that have this mode. Okay, so that's what we could call particles and antiparticles. For now, we don't know yet because we did not compute the charges of these particles, but we see that they play the same role in terms of energy. So both contribute the same factor, omega p.